The story of Earth's water begins with the formation of the planet itself. About 4.5 billion years ago, Earth formed from the dust and gas surrounding the young Sun in what is known as the protoplanetary disk. As these particles collided and stuck together, they gradually built up the early Earth. During this formative period, the planet was a molten mass, characterized by intense volcanic activity and frequent impacts from other celestial bodies. As Earth cooled, a solid crust formed over the molten interior, and volcanic activity began to release gases into the atmosphere. This early atmosphere was primarily composed of water vapor, carbon dioxide, and nitrogen, with trace amounts of other gases. The question of how Earth's water originated is crucial in understanding our planet's early history. One prominent theory suggests that Earth's water came from icy comets and asteroids that collided with the planet. These celestial bodies, composed of water ice and other volatiles, deposited their contents onto the young Earth. Alternatively, water may have been released from the Earth's mantle through volcanic outgassing. This process would have involved the release of water vapor and other gases trapped within the planet's interior. As the planet continued to cool, the water vapor in the atmosphere began to condense, forming the first clouds. Once the temperature dropped sufficiently, rain began to fall, and the accumulated water collected in low-lying areas, forming the primordial oceans. This process likely took place over hundreds of millions of years, gradually creating vast bodies of water that covered much of Earth's surface. The early oceans were acidic due to dissolved carbon dioxide and other volcanic gases. Over time, chemical reactions between the rainwater and the volcanic rocks helped neutralize this acidity, leading to the development of a more stable ocean chemistry. The formation of oceans was a pivotal moment in Earth's history, providing a stable environment where life could eventually emerge. Plate tectonics, the movement of Earth's lithospheric plates, played a significant role in shaping the distribution of water bodies on the planet. As tectonic plates shifted, they created mountain ranges, ocean basins, and other geological features. The movement of these plates also contributed to the formation of rift valleys and ocean trenches, which further influenced the distribution and flow of water. The ongoing movement of tectonic plates continues to shape Earth's surface, leading to the creation of new landforms and altering the locations of existing water bodies. For example, the formation of the Himalayas influenced the flow of rivers in Asia, while the opening of the Atlantic Ocean reshaped the distribution of marine life and ocean currents. With the formation of oceans and the stabilization of Earth's atmosphere, the planet's water cycle began to develop. The water cycle is a continuous process involving evaporation, condensation, precipitation, infiltration, and runoff. This cycle regulates the distribution of water across different environments and plays a crucial role in supporting life on Earth. The water cycle is driven by solar energy, which causes water to evaporate from oceans and other bodies of water. As water vapor rises into the atmosphere, it cools and condenses to form clouds. Eventually, the condensed water falls back to Earth as precipitation, replenishing rivers, lakes, and groundwater supplies. This cycle has been fundamental in maintaining Earth's climate and supporting diverse ecosystems throughout the planet's history. The advent of life on Earth also influenced the planet's water chemistry. Early microorganisms, such as cyanobacteria, began to photosynthesize, producing oxygen as a byproduct. This process gradually increased the levels of oxygen in the atmosphere, leading to the formation of the ozone layer and the stabilization of Earth's climate. The presence of oxygen in the oceans also facilitated the formation of more complex organic molecules, laying the groundwork for the development of diverse life forms. The interaction between life and water has been a dynamic and evolving process. As life forms adapted to different environments, they influenced the chemistry of oceans, rivers, and lakes, shaping the course of Earth's biological and geological history. The water cycle, also known as the hydrological cycle, is a continuous process that moves water through various states and locations on Earth. This cycle is essential for regulating the planet's climate, supporting ecosystems, and providing freshwater resources. The main components of the water cycle include evaporation, condensation, precipitation, infiltration, and runoff. Understanding each of these processes is crucial to appreciating how water circulates and sustains life on Earth. Evaporation is the process by which water changes from a liquid to a vapor. This transformation occurs when water molecules at the surface of bodies of water, such as oceans, lakes, and rivers, gain enough energy from the sun to overcome intermolecular forces and escape into the atmosphere. Evaporation is driven primarily by solar energy, which heats the water and accelerates the rate of evaporation. Evaporation also occurs from other surfaces, such as soil and vegetation, through a process called evapotranspiration. Plants release water vapor into the atmosphere through tiny openings in their leaves called stomata. This contributes significantly to the total amount of water vapor in the atmosphere and plays a key role in the water cycle. Once water vapor rises into the atmosphere, it cools and condenses to form tiny droplets. This process is called condensation. As water vapor cools, it changes from a gaseous state back into a liquid, creating clouds. Condensation occurs when the air reaches its dew point, the temperature at which air becomes saturated with moisture. Cloud formation is influenced by several factors, including temperature, humidity, and air pressure. Different types of clouds, such as cumulus, stratus, and cirrus, form under varying atmospheric conditions. Clouds play a critical role in the water cycle by acting as reservoirs of water vapor, which can eventually lead to precipitation. Precipitation is the process by which water falls from the atmosphere back to Earth's surface. It occurs when the droplets in clouds combine and grow larger until they are heavy enough to overcome air resistance and fall to the ground. Precipitation can take various forms, including rain, snow, sleet, and hail, depending on the temperature and atmospheric conditions. Rain is the most common form of precipitation and is essential for replenishing surface water bodies and groundwater supplies. Snow occurs when temperatures are below freezing, and the water vapor in clouds forms ice crystals. Sleet and hail are less common and occur under specific atmospheric conditions. The type and amount of precipitation influence the distribution of freshwater resources and the health of ecosystems. Infiltration is the process by which water on the ground surface enters the soil and moves downward. This process is influenced by soil properties, such as permeability and texture. Once water infiltrates the soil, it moves through the soil layers in a process called percolation. This movement of water through the soil contributes to the replenishment of groundwater supplies. Groundwater is stored in aquifers, which are permeable rock or sediment layers that can hold and transmit water. Aquifers provide a vital source of fresh water for many regions and are crucial for drinking water, irrigation, and industrial use. The interaction between surface water and groundwater is a key component of the water cycle, affecting the availability and quality of freshwater resources. Runoff is the movement of water across the land surface and its eventual return to oceans, lakes, and rivers. Runoff occurs when water from precipitation or melting snow exceeds the infiltration capacity of the soil, causing it to flow overland. This process can lead to the formation of streams and rivers, which transport water to larger bodies of water. Runoff plays a significant role in shaping the landscape, contributing to erosion and sediment transport. It also affects water quality by carrying pollutants and sediments from the land into water bodies. Proper management of runoff is essential for preventing soil erosion, reducing pollution, and maintaining healthy aquatic ecosystems. The water cycle plays a crucial role in regulating Earth's climate. By transferring heat and moisture between the atmosphere and surface, the water cycle influences weather patterns and temperature. Evaporation and condensation processes release and absorb heat, affecting local and global climate conditions. For example, the formation of clouds and precipitation can influence temperature by reflecting sunlight and trapping heat. The distribution of water vapor in the atmosphere also affects greenhouse gas concentrations, contributing to climate change. Understanding the water cycle's impact on climate is essential for addressing environmental challenges and predicting future climate scenarios. Human activities have a significant impact on the water cycle. Urbanization, deforestation, and agriculture can alter natural water flow patterns and affect water quality. For example, the construction of buildings and roads can increase runoff and reduce infiltration, leading to more frequent flooding and reduced groundwater recharge. Pollution from industrial activities, agriculture, and wastewater can contaminate water sources, affecting both surface water and groundwater quality. Climate change, driven by human activities, is also altering precipitation patterns and affecting the water cycle's balance. Addressing these impacts requires sustainable water management practices and efforts to mitigate environmental degradation. Freshwater is essential for all known forms of life, yet it constitutes a small fraction of Earth's total water supply. Approximately 97.5% of Earth's water is saltwater, primarily found in the oceans. The remaining 2.5% is freshwater, but not all of this is easily accessible for human use. Freshwater is distributed across several key sources: glaciers and ice caps. About 68.7% of the planet's freshwater is locked away in glaciers and ice caps, primarily in polar regions and high mountain ranges. This water is not readily accessible but serves as a critical long-term reservoir. Groundwater. Approximately 30.1% of freshwater is stored underground in aquifers. Groundwater is a significant source of drinking water and irrigation for agriculture. Surface water. Only about 1.2% of Earth's freshwater is found in surface water bodies, such as rivers, lakes, and wetlands. Despite its small proportion, surface water is crucial for immediate human needs. Rivers and streams. Rivers and streams are dynamic sources of freshwater that flow from higher elevations to lower areas, eventually emptying into oceans or lakes. They are vital for drinking water, agriculture, and transportation. Lakes and reservoirs. Lakes are inland depressions that hold freshwater, while reservoirs are artificial lakes created by damming rivers. Both are important for storing water for human use, recreation, and supporting ecosystems. Wetlands. Wetlands, including marshes, swamps, and bogs, act as natural filters, trapping pollutants and providing habitat for diverse species. They also help in flood control and groundwater recharge. Effective management of freshwater resources is critical due to several pressing challenges. Water scarcity. Many regions around the world face water scarcity, where the demand for water exceeds the available supply. This can be due to natural factors, such as arid climates, or human activities, like over-extraction and pollution. Pollution. Water pollution from industrial discharge, agricultural runoff, and wastewater can contaminate freshwater sources, making them unsafe for consumption and harming aquatic ecosystems. Over-extraction. Excessive withdrawal of groundwater and surface water for agricultural, industrial, and domestic use can deplete resources faster than they can be replenished, leading to long-term shortages. To address these challenges, sustainable water management practices are essential. These strategies include water conservation, implementing measures to reduce water use, such as using water-efficient fixtures, fixing leaks, and promoting water-saving behaviors. Pollution control, enforcing regulations to limit the discharge of pollutants into water bodies and investing in wastewater treatment technologies to protect water quality. Integrated water resources management, IWRM, adopting a holistic approach that considers the interconnectedness of water sources, land use, and social needs. IWRM promotes collaboration among stakeholders and ensures the sustainable use of water resources. Investing in infrastructure, developing and maintaining infrastructure for water storage, distribution, and treatment to improve water accessibility and reduce losses. Several regions around the world exemplify the challenges of water scarcity. Sub-Saharan Africa. Many countries in this region face severe water shortages due to a combination of arid conditions, population growth, and inadequate infrastructure. Efforts to improve access to clean water include building wells, developing rainwater harvesting systems, and promoting water conservation practices. The Middle East. Countries like Saudi Arabia and Jordan experience extreme water scarcity due to arid climates and high water demand. Solutions include desalination technologies, which convert seawater into potable water, and regional cooperation to manage shared water resources. California, USA. Persistent drought conditions and high water demand have led to significant water management challenges in California. The state has implemented measures such as water rationing, investment in water recycling, and the construction of new reservoirs to address these issues. Climate change significantly impacts freshwater resources by altering precipitation patterns, increasing the frequency of extreme weather events, and affecting snow and ice melt. Changes in climate can lead to altered precipitation patterns. Shifts in rainfall patterns can result in more intense storms and prolonged droughts, affecting the availability of freshwater. Melting glaciers and ice caps. the melting of glaciers and ice caps contributes to rising sea levels and changes in freshwater availability for regions dependent on glacial melt. Increased evaporation. Higher temperatures can increase evaporation rates, reducing the amount of water available for replenishment. Looking ahead, addressing the challenges of freshwater management will require innovation and cooperation. Advancements in water technology. Innovations such as advanced desalination, water recycling, and smart irrigation systems can enhance water efficiency and availability. Global cooperation. International agreements and partnerships are essential for managing transboundary water resources and addressing global water challenges. Public awareness and education. Raising awareness about water conservation and the importance of sustainable management can drive positive change at both individual and community levels. Oceans cover more than 70% of Earth's surface, making them the largest and most influential component of the planet's climate system. The world's oceans are divided into 5 major basins: the Pacific, Atlantic, Indian, Southern, and Arctic oceans. Each of these oceans plays a vital role in regulating climate and supporting global biodiversity. The immense size and depth of the oceans contribute to their significant role in Earth's climate system. The average depth of the oceans is about 3,800 meters, 12,500 feet, with the deepest part, the Mariana Trench, reaching over 11,000 meters, 36,000 feet. This vast expanse of water influences weather patterns, temperature distribution, and the overall climate. Ocean currents are large-scale movements of water that circulate through the world's oceans, driven by factors such as wind, temperature, salinity, and Earth's rotation. These currents play a critical role in distributing heat around the planet, affecting both regional and global climates. Surface currents. Surface currents, driven by wind patterns, move warm water from the equator toward the poles and cold water from the poles toward the equator. Major surface currents include the Gulf Stream, the Kuroshio Current, and the Antarctic Circumpolar Current. These currents influence coastal climates, such as the temperate climate of Western Europe influenced by the Gulf Stream. Deep ocean currents. Also known as thermohaline circulation, deep ocean currents are driven by differences in water density, which are affected by temperature and salinity. These currents, such as the Atlantic meridional overturning circulation, play a key role in regulating Earth's climate by redistributing heat and influencing carbon dioxide levels in the atmosphere. Oceans act as a major sink for atmospheric carbon dioxide, CO2, absorbing about a quarter of the CO2 emitted by human activities. The ocean's ability to absorb CO2 helps mitigate the impacts of climate change by reducing the concentration of greenhouse gases in the atmosphere. Biological pump. The biological pump is a process in which marine organisms, such as phytoplankton, absorb CO2 during photosynthesis. When these organisms die, their remains sink to the ocean floor, sequestering carbon in deep sea sediments. This process helps regulate atmospheric CO2 levels and influences global climate patterns. Oceanic uptake. Oceans absorb CO2 directly from the atmosphere through physical and chemical processes. This uptake of CO2 affects ocean chemistry and can lead to ocean acidification, which has significant implications for marine ecosystems and species. Sea level rise is one of the most visible consequences of climate change, driven by 2 main factors: thermal expansion of seawater and the melting of glaciers and ice caps. Rising sea levels pose a range of challenges to coastal communities and ecosystems. Thermal expansion. As global temperatures increase, seawater warms and expands. This thermal expansion contributes to rising sea levels and can lead to flooding of low-lying coastal areas. Melting glaciers and ice caps. The melting of glaciers and ice caps adds additional water to the oceans, further contributing to sea level rise. This process affects polar regions and can lead to significant changes in ocean circulation and weather patterns. Impacts on coastal areas. Rising sea levels can lead to coastal erosion, increased flooding, and the loss of valuable habitats such as mangroves and wetlands. Coastal communities may face challenges related to infrastructure, property damage, and displacement. Ocean acidification is a consequence of increased CO2 levels, as the oceans absorb more carbon dioxide and form carbonic acid. This leads to a decrease in the pH of seawater, affecting marine organisms and ecosystems. Effects on marine organisms. Acidic conditions can negatively impact marine organisms with calcium carbonate shells or skeletons, such as corals, mollusks, and some plankton species. These impacts can disrupt marine food webs and biodiversity. Coral reefs. Coral reefs, which are highly sensitive to changes in pH and temperature, are particularly vulnerable to ocean acidification. Coral bleaching and reduced calcification can lead to the decline of reef ecosystems, affecting the many species that rely on them for habitat and food. Ocean currents influence weather patterns and climate by redistributing heat and moisture. Changes in ocean currents can lead to alterations in regional weather conditions, such as increased rainfall or drought. El Niño and La Niña. El Niño and La Niña are climate phenomena associated with variations in ocean temperatures and currents in the central and eastern Pacific Ocean. These phenomena have widespread effects on global weather patterns, including changes in precipitation, temperature, and storm activity. Monsoon systems. Ocean currents play a role in driving monsoon systems, which are characterized by seasonal shifts in wind patterns and precipitation. The interaction between ocean temperatures and atmospheric conditions can influence the intensity and duration of monsoon rains. Human activities have a significant impact on ocean health, affecting everything from pollution to overfishing and habitat destruction. Addressing these impacts is crucial for maintaining the health and function of ocean ecosystems. Pollution. Pollution from land-based sources, such as plastics, chemicals, and nutrients, can harm marine life and ecosystems. Efforts to reduce pollution and manage waste are essential for protecting ocean health. Overfishing. Overfishing can deplete fish populations and disrupt marine food webs. Sustainable fishing practices and the establishment of marine protected areas are important for conserving marine resources. Habitat destruction. Activities such as coastal development and trawling can damage important marine habitats, including coral reefs, mangroves, and seagrass beds. Conservation efforts and habitat restoration are needed to preserve these vital ecosystems. Looking ahead, addressing the challenges facing the oceans will require a combination of scientific research, policy initiatives, and public awareness. Key areas for action include climate mitigation. Reducing greenhouse gas emissions is crucial for addressing climate change and its impacts on the oceans. International agreements and efforts to transition to renewable energy sources can help mitigate these effects. Marine conservation. Protecting marine environments through the establishment of marine reserves, sustainable fisheries management, and pollution control measures is essential for maintaining ocean health. Public engagement. Raising awareness about ocean issues and encouraging sustainable practices can drive positive change and support conservation efforts. Water scarcity occurs when the demand for water exceeds the available supply or when water quality is insufficient to meet the needs of people and ecosystems. It can be categorized into two main types: physical water scarcity. This occurs when there is not enough water to meet the needs of a region due to limited natural resources or environmental conditions. Regions with arid climates or low rainfall are often affected by physical water scarcity. Economic water scarcity. This arises when water is available but is not accessible to people due to infrastructure, financial, or institutional constraints. Economic water scarcity can occur in both water-rich and water-poor regions, often affecting developing countries with inadequate water management systems. Several factors contribute to the growing issue of water scarcity. Population growth. Rapid population growth increases the demand for water for drinking, agriculture, and industry. As populations expand, the pressure on existing water resources intensifies, leading to competition and potential shortages. Climate change. Changes in climate patterns, including altered precipitation and increased evaporation rates, affect the availability of freshwater resources. Extreme weather events such as droughts and floods can exacerbate water scarcity issues. Water pollution. Pollution from agricultural runoff, industrial discharges, and wastewater can contaminate freshwater sources, making them unsafe for consumption and reducing the availability of clean water. Over-extraction. Excessive withdrawal of water from rivers, lakes, and aquifers for agricultural, industrial, and domestic use can deplete resources faster than they can be replenished, leading to shortages and environmental degradation. Water scarcity has far-reaching consequences for both human societies and the environment. Health impacts. Lack of access to clean water can lead to the spread of waterborne diseases, such as cholera and dysentery. Contaminated water sources pose significant health risks, particularly in developing regions with inadequate sanitation and healthcare facilities. Economic impacts. Water scarcity can affect agricultural productivity, reduce industrial output, and increase the cost of water for consumers. Economies reliant on water-intensive industries, such as agriculture and manufacturing, may experience reduced growth and economic instability. Environmental impacts. Reduced water availability can lead to the degradation of ecosystems, including wetlands, rivers, and lakes. This can result in the loss of biodiversity, altered habitat conditions, and diminished ecosystem services, such as water filtration and flood regulation. Social impacts. Water scarcity can lead to conflicts over water resources, migration, and displacement. Communities facing severe water shortages may experience social tensions and struggle to meet basic needs, leading to inequalities and increased vulnerability. Examining specific regions affected by water scarcity provides insight into the challenges and solutions. The Middle East and North Africa, MENA. The MENA region is characterized by arid and semi-arid climates, leading to significant water scarcity challenges. Countries such as Jordan and Saudi Arabia face severe water shortages and rely on desalination and water reuse technologies to meet their needs. Regional cooperation and investments in water-efficient technologies are essential for addressing these challenges. South Asia. Countries like India and Pakistan experience water scarcity due to high population densities, over-extraction of groundwater, and seasonal variability in precipitation. Water management strategies, such as improving irrigation efficiency and enhancing water storage, are crucial for addressing water stress in this region. Sub-Saharan Africa. Water scarcity in sub-Saharan Africa is exacerbated by factors such as population growth, climate change, and limited infrastructure. Efforts to improve access to clean water include drilling wells, implementing rainwater harvesting systems, and enhancing sanitation facilities. Effective strategies for mitigating water scarcity involve a combination of technology, policy, and community engagement. Water conservation. Promoting water-saving practices, such as reducing water use in households and industries, and adopting efficient irrigation techniques can help alleviate pressure on water resources. Improved water management. Implementing integrated water resources management (IWRM) approaches can enhance the sustainable use and allocation of water resources. IWRM considers the interconnectedness of water sources, land use, and social needs, fostering collaboration among stakeholders. Investments in infrastructure. Developing and maintaining infrastructure for water storage, distribution, and treatment can improve water accessibility and reduce losses. Investments in technology such as desalination and water recycling can also augment water supplies. Public awareness and education. Raising awareness about water conservation and the importance of sustainable water management can drive positive change at individual and community levels. Educational programs and outreach initiatives can promote water-saving behaviors and foster a culture of conservation. Effective policy and governance are critical for addressing water scarcity. Regulations and standards. Implementing regulations and standards for water use, pollution control, and resource management can ensure the sustainable use of water resources and protect water quality. International cooperation. Addressing transboundary water issues requires cooperation between countries sharing water resources. International agreements and collaborative efforts can help manage shared resources and resolve conflicts. Community involvement. Engaging local communities in water management decisions and practices can enhance the effectiveness of water conservation efforts and ensure that solutions are tailored to local needs and conditions. Looking ahead, addressing water scarcity will require innovative solutions and sustained efforts. Technological advancements. Continued research and development of water-saving technologies, such as advanced irrigation systems, water-efficient appliances, and smart water management systems, will be crucial for meeting future water needs. Climate adaptation. Adapting to climate change and its impacts on water resources will require strategies such as improving water storage, enhancing flood management, and developing resilient infrastructure. Global and local initiatives. Collaborative efforts at both global and local levels are essential for addressing water scarcity. International partnerships, national policies, and community-driven initiatives can contribute to sustainable water management and ensure access to clean water for all.